Dear students, I hope you are well. We are close to the end of the semester. Hopefully, next week I will be giving you exam 4. In my previous lecture, lecture 14, I discussed with you the spectra of D2 system in very good details. We interpreted the spectra of D2. There were two bands very clearly visible in that, and there was a third band which was not visible, it was hidden, and that was a high energy band. Now, without going into any further details of the previous lecture, I'm going to now in this lecture start with the D3 system. It is plus minus the same way. If you have understood D2, there is no problem understanding D3 system. We will do the interpretation of the spectra the way we did it for D2. By interpretation of the spectra, I mean whatever spectra we see. For example, this is a spectra. Okay, in its analysis interpretation, what we will do is we'll see why it is giving two bands, why these two bands are prominent, why this band is not, why this band is coming at higher energy and this is coming at lower, and things like that. So we did it for D2, we will do it for D3 as well. We will also in this lecture use the transition energy ratio diagram. This is a new thing, very easy and very simple for solving a delta octahedral over B value. Okay, now let's start with interpretation of the spectra of D3. Here I'm giving you configuration of D3. Okay, one, this is an octahedral field T2G, T2G. Well, this is half filled, so it should be A. Okay, represented with A. And then there are 3 unpaired electrons, so it should be 4 here. Okay, spin degeneracy. So A2G4, this is the ground state. Second configuration which can come for D3, 2 electrons here and 1 goes up. Now this is not half filled. Okay, there are 2 electrons in the 3 orbitals, so it will be represented with T. There are 2 unpaired electrons, so 3 here. There is only 1 electron in the EG set, so spin degeneracy 2. Similarly, 1 electron here and 2 electron up there. This will be capital T. Okay, 1 electron 2 and 2G. Okay, so that is the excited state. This is also excited state. Okay, so this is how you represent it. So see here, I have multiplied T with E. I have written here. So T multiplied A is again T. Okay, no, sorry. This is T multiplied by E. Okay, so it will give a number of states. But here you see T multiplied by A is equal to T. Now, in your book, Lever book, on page 1.6, ground state terms and the excited state terms, they are given. Terms for D3 and D7 system are shown. This is what is recorded. Okay, this is a D3 system, so it's a quartet. So this is the ground state quartet and P4 excited state. I think you can find it. Now this is the Tanabe-Sugano diagram. It is available and given in the diagrams. I have shown it on page 4 of your notes. and it is here, Tanabe-Sugano diagram. It contains, remember, A to G. This is the ground state, okay, and then another quartet, another quartet, another quartet. So this is the Tanabe-Sugano diagram. I've shown it here, okay, as well. Okay, ground state, quartet A to G, quartet T to G, quartet A1, and so forth. Okay, now if you notice that this is T to G3, the ground state, good. And then on the right hand side is written, okay, it is T2G6 and EG this. So what is it? T2G3 system is equivalent to, okay, D8 system. D3 system is equal to D8 system. The same sort of thing we did in D2 system. Here also it is T2G EG. Okay, this is equivalent to T2G5 and EG3. I will prove that here. Come here. Once again, you note that T2G6 and EG2 is written in front of T2G3. This one. And similarly, this is written in front of this. This is written in front of this. The above equivalence is based on this, which you have already learned. Dn is equivalent to D5 plus n. So D3 will be equivalent to D8 system. Okay, I have made a question here. Prove that D8, this thing, is equivalent to D3, this thing. Okay, T2G5, EG3 is equivalent to this. How do we do it? Very simple. This is equal to what? This is T2G5, so I have split it into two, T2G3 and T2G2. Okay, done. EG3 I have split into two, EG2 and EG1. Remember, this is half filled, so A. This is half filled, so A. Okay, A multiplied by this is, okay, it doesn't affect it. And this A multiplied doesn't affect it. So what we will get is the final result, okay, that this is equal to this. I have shown it in some details here. You can read it. So expected allowed transitions mu1, mu2 and mu3 in T3 system. Okay, here is the Tanabe-Sugano diagram. It is given on the page 4, okay, of the notes which I have. Okay, now this is the diagram now. So it's very clear the spin allowed transitions, how many they are? Quartet to quartet, quartet to quartet, quartet to quartet. Rest are doublets. Doublets. So their band will come, but that will be a weak band. That will be a weak band. Now here, I think I'm going to explain this with the help of an example, and I have taken chromium 3 complex. It has 3 strong bands. Sorry. It has 3 strong bands. I will show you. It is on page 6. One here, and one here. Okay. The question is determine delta octahedral over delta octahedral B and percentage covalent. Delta octahedral is ligand field parameter, B is Rocca parameter, interelectronic repulsion pair, and the covalent character between the metal and ligand bond. Solution very simple. D3 systems. So we, from Tanabe-Sugano diagram, which I have shown you before on page for spectral study. Okay, the very first step is we convert the wavelengths, which are in nanometer, to reciprocal centimeter. You can read it. It is just simple. 1 centimeter is so much nanometer. I have done this conversion. Okay, and you can do it. From the diagram, what is very clear, the thing which is very clear is there should be 3 band, not 4, not 5. This is the important thing. You are learning electronic spectra. So 3 clear bands one can see. The other bands are also there, but then they are weak. Okay, so this is very true. We predicted from this diagram, Tanabes one of 3 bands, and this is very true. We get 3 bands. Okay, here are those. So this is the beauty of this course. Whatever we get in the from the instrument in the spectra, we can predict it beforehand. So here is spectra of the chromium 3 ammonia complex. We have these 2 bands very clear. The third band comes somewhere here. Okay, it is at high energy. See, this is 8,000, this is 13,000, this is 20, then there's 25, maybe it is somewhere at 30,000. So it's hidden. The second thing is that there is a very strong band, we call it charge transfer band. I wish I had time enough to give you a lecture on charge transfer band, but it is hid under this, okay, like this. So there is a third band, you can see it is a magnified, okay. It is from A to G quartet to doublet. It is a spin forbidden transition, and so a small band. Okay, its E value is small. E value of this is large, strong band. 2 strong bands are quite visible. This is one which comes at 8,000 reciprocal centimeter, and the other comes at the third band is not clear. Okay, a determination of experimental ratio. This is important. You did it in D2. We will do it for D3, and I think that should make it very. The ratio between mu2 and mu2, energy of mu2, E2, and E1 energy of mu1, okay, that is okay, equal to E2 over, I have written these transitions also to make the thing clear. So E2 over E1. What's the value of E2? This. What's the value of E1? This. Okay. So if we divide it, it comes out to be 1.7. So this is the value of E2 over E1. That was the step. What we are doing? We are determining the experimental energy ratio. So we have done it. Where from I got this? From the spectra experiment. Okay, what is the value we got it? 1.7. So finished. This job is finished. We got it. So next step is going to be finding out theoretical determination of theoretical energy ratio. Okay, this is a bit tedious one, difficult one, but I think you can. We do it by hit and trial method. I'm reminding you, you learned it. Okay, in my last lecture 14, we are going to repeat it for D3. First spin allowed transition is mu, this one. The second is this one, E2. The third is this one. Okay, in Tanabe-Sagano diagram, we find out the value of the next higher energy mu2 at the same values, this. Okay, to begin with, first of all, like before, okay, we will use the Tanabe-Sagano D3 and find out values of energies of the lowest energy transition, E1, okay, over B. Where from I get it? Here it is. See the diagram. Here is the scale E over B. So E1 will be this one transition, the lowest energy transition, this one quartet to quartet, this one. What is the energy of this? Okay, you go from here and then you make a left. Whatever is written here is the energy, okay, of the first transition, and that will be E1 over B. This is what I have written there, okay. For the second transition, this is the energy. From here, I go to the second transition here, this one, and then I make a left. This is what I wrote in my previous lecture. So I think I want to go to this table, which is important. What I was talking verbally, it is shown here. So we take different values of delta octahedral over B. Here you see that. Okay, I've written find out values of energy of the lowest energy transition E1 at different values of delta octahedral like 10, 50. Delta octahedral 10, 20, 30, 40. What is the E1 value? For 10 it is 10. For 20 it is 20. See this from here. Please, let's come here. When delta octahedral is equal to 10, it's 10 is here. Okay, go up and then make a left. What is the energy on the left side? 10. E1 over B is 10. Then you go to 20. This is, no, you don't, yeah, delta octahedral 20. Okay, for this 20, you will stay at this one. First transition we are talking about. So you make a left and you will find that this will come at E1 for 20, it is 20. Okay, is it, this is D3 for 30. Okay, in this plot it is it's not reflecting it, but anyway, this is how we do it for 40. I don't know what is what is wrong here. Okay, see, this is table 1 where I have recorded the values of delta octahedral over B. Okay, for example 10. So at 10, what is the value of E1 over B? This we find out from Tanabe-Sugano diagram. So come to Tanabe-Sugano diagram. This is Tanabe-Sugano of D3. So this is 10, okay, circle I, and go up to the first transition, mu1, this one, and then make a left here, okay. So it is coming, okay, no, sorry, this is, yeah, no, it comes here. This circle comes here, was putting, so this goes here, like this, and so this is 10. Now let's come to second one, delta octahedral 20, E1, okay, over B, okay, you will see it's going to be 20. Here is 20, so I'm going up like this, from here, in, here it is. This is your mu1, first transition, make a left, okay, we come here and this is 20. Okay, similarly at 30, okay, I have recorded value 30, so this is 30, so let's go up like this, and this is the first transition, so you make a left and you will come at 30. For 40 it is 40. Let's see the first transition, not the second one. You go up like this. Okay, I hope I have not lost it. And it is here. And you make a left, and this is again 40. So we record it. Then we go to the E2. Where is E2? E2 is this one, second. Okay, from here to the second line. Okay, from A2G4 to T1G4, this one. So at 10, let's see what is the value of. We go up here, we don't stop here, we go and stop here, okay, on the second line. 10, 10, and this is equal to 16. I'll put 16.5, but then, okay, it is okay. 16 or 16.5, this one. The 20, for 20, I have recorded 29 E2 value, okay. 20, now let's go. From here, we go up here and stop here. Okay, and then we make left. Here, we come here. What is that? 29. It is 29. Okay, one. Similarly, you do this and you do this. Okay, the next step is finding out value of E1 over E2. Oh, this is simple. Divide the value of E2 with this one. Okay, and you will get this. Divide this value with this one. Okay, you will get this. And these are going to be, I'm going to, in order to evaluate the value of delta octahedral B, that will precisely, okay, now here is another thing which I want to do. I should not jump from here, I go to the table 2. Now this was incremented from 10, with increment 10, it becomes 20, 30 and 40. So the value which we are getting here is 1.7 of E1 over E2. Now, in order that we find out exactly, precisely, so what we do is we give increment, smaller increment, relatively smaller increments, and find out that what is the value of delta, E2 over E1, which is exactly or very closely equal to the experimental value which we found with the help of spectra. Remember, that was 1.7. So although we are getting here 1.7, but then we want to make it more precise. So what I have done, increment of 5 instead of 10. 5, 10, 15, 20, and we do the same exercise. We get these values. For E2, we get these values, and see for 5, delta octahedral equal to B equal to 5, it is 1.7. Experimental value is 1.7, so we reject it. See this one, 15, at 15, delta octahedral, it is 8.2. Experimental value is 1.7, we reject it. 20, it comes, we reject it. Okay, at 10, it is 1.7, so we find it out. How we find? Theoretically, we have found out. Table 2, we find that at delta octahedral equal to 10, the value of E2 over E1 is equal to 1.7. So theoretically, value of delta at which the energy ratio E2 matches with the experimental value 1.7 is 10. We have found it out. So rest of the things are very simple. I have written once the value of this thing, delta octahedral, is determined, we can easily carry out following. And what is that? Determination of the ligand field parameter, delta octahedral or DQ. We can do the assignments of the bands. We can determine Raka parameter, B, interelectronic repulsion parameter, and the covalent character between metal ligand and bond. Now I'm going to do this one by one. How do we do the assignment of bond to transition? Since theoretically and experimental energy ratio values match very well, therefore we can safely conclude that this transition, okay, is correctly assigned to, this is the second transition, please, mu2, 13,600 reciprocal centimeter. Remember, this was the experimental, okay, value. So we said that, okay, let us suppose that this is mu2 and let us suppose this is mu1. So now that we see that the experimental value which comes of mu2 over mu1, 1.7, we have determined it theoretically as well, and that is 1.7. So therefore we will say whatever we supposed is correct. So that is how we verify and assign bands to the transition. Whatever assignment we have done, this assignment is mu2 and the other one is mu1. Okay? So the determination of the Raka parameter, that is B. Again, you will see it's very, very simple. Raka parameter delta octahedral will be equal to 10. Okay. We know that delta octahedral of B is equal to 10. We have found it out before because at this value, our energy ratio value comes 1.7. Okay. So at data this, the value of E1 over B is equal to 10. I think we must go back to this table. See table 2, I have, okay? At this value, in table 2, the value of E1 over B, okay, this is E1 over B and this is equal to 10. At delta octahedral equal to 10, this value is equal to 10. So I think this is an important table 1 and table 2. Table 2 is more important for this, okay? So we find it out. Okay. Remember, we know the energy of E1. Where is the energy E1 written? Okay, let us see. E1 is equal to so much. So what we will do, we'll take this value, put it here, and finished. The whole thing is finished. Now you will see that. Next step. And E2 over, sorry, I have just, okay, E1 is equal to, so E2 over B is equal to 16 at 10. See this one. At 10, value of delta octahedral equal to 10. E1 value is equal to 10. E2 value is 16.5. This is what I mentioned here. Okay. So see table 2. So delta